Um, we stopped on the acid-base definitions by three scientists and four scientists, and Arrhenius, Prosen, and Lowry, two scientists, and Lewis, so the fourth one. So, but anyway, and we went through the acid base and their conjugated acid base, correct definitions. Now today we'll learn how about naming those acids and bases. So today we'll naming acids and bases. So let's start with the acids because that's more comprehensive than the base. The base is straightforward. Bases are straightforward. So we name the acids. So we have to start with there are several types of naming those acids. The first one, acids without oxygens. Acids without oxygen. So those are such they come just with the hydrogen or proton and the another anion. So you start with the hydro. So this is hydro. Whenever those without, you start with hydro. And then the next one here, then is be the next atom will be chlorine, correct? Chlorine. You take the I and E out, add ic acid. So that's the first type without. So how we name them? The first hydro for the hydrogen, and then the second atom there will be chlorine. Take the I and E out, add ic acid. So, and this one here will be the same token here. Will be hydro, and then you have fluoric. Take fluor and then fluoric. So we took the I and E out. So take the I and E out. Fluoric acid. Correct? We have, this is hydro, bromic acid. Correct? And the other one is HI, for example, hydro iodic acid. So always ic acid, ic acid. So those are acids that they don't have an oxygen inside them. There's some strange exception here. Exception for we have an acid that has no oxygen, but this is an acid too, weak acid. This is H2S, call it H2S. So this acid you cannot say hydrogen and then say sulfuric. We cannot say hydrogen like two hydrogens, correct? You will say the name here. You name it like. Let me show you here, guys. You cannot say this is hydrosulfuric acid. This name is wrong. Okay, this name is not correct. We will not say, we can use it, but that's not, because sulfuric acid is different acid than this. So what we do with this, we'll say, well, that's hydrogen sulfide or dihydrogen sulfide. Just, we know an acid, but it is not. It's not used with ic acid, sulfuric acid. We know it's hydrosulfuric acid. We'll not do that. So good. Okay, so it does not have an oxygen. So we'll name it as we name a covalent compound, dihydrogen sulfide. Okay, guys, that's the first one. Everybody has this? Everybody has this? Okay, let's take this one out. And now we look at the acids. Um, they do have number two. They do have oxygens. Acids with oxygen. Now, of course, acid has hydrogen, but some of them they have no oxygen, as we have seen. But there are some acids that have oxygens. Well, we have HNO3, H2SO4, H3PO4. Okay, those are the major ones. In this sense, we have hydrogen and oxygen there. So we have oxygen, we have hydrogen. So you have hydrogen, you have oxygen, you have hydrogen, you have oxygen. So how we name this? We name this one here to the central atom. So get this one here, central atom. Central atom is nitrogen. You transfer nitrogen to nitric, correct? So take this one here out. Nitrogen, take this one out here and add ic acid. So this one here will be named then, this one here will be named as nitric acid, ic acid. So instead of nitrogen, so nitrogen will modify to nitric and then to nitric and then add nitr, and then add ic acid, nitric acid. So how about this one here? This one will be then, this is sulfur, correct? Sulfuric acid, correct? Sulfuric acid. So let me write this so you can see it here much better. So sulfuric acid. How about here? That's phosphorus, correct? Start with phosphoric acid. So those are the oxygen. You always look at the central atom and then name the acid after the central atom by modifying the central atom and then add ic acid. So not phosphorus, phosphor, then add ic acid. Nitrogen, niter, ic acid. Sulfur, ic acid, and so on. So this is another type. Now, sometimes we have the oxygen. This is the standard naming. All those are standard naming. But sometimes you have other type that's the oxygen is less. Oxygen is less. So then we have special naming for those acids. They have oxygen less. Okay, so we'll take those ones as our standards, and then we can name the ones they have less. So everybody has this. Everybody has this. Okay, good. Thank you. So let's take this one out. Number 3, acids with less or more oxygen. So, for example, I have here HNO3. I have here HNO2. I have here HNO. So this is the standard. Okay, that's the standard acid. So we call it what? Nitric acid, correct? Less, one oxygen less, one oxygen less. So we call it nitrous acid. So ic acid, this is ic acid. This is acid. Correct? Now, go here and one oxygen less even, will, anytime less means hypo, correct? Hypo nitrous. Then this one has two, this one has one. Hyponitrous acid. Get the idea? We'll do another example. Okay? Everybody has this? No? Okay. Yeah, just cool yourself down. Okay, so can everybody has it? Everybody has it? Okay. Let's take this one out and then because this is very confusing and sometimes they bring it in ICS exams. So let's take another example. Another example with the sulfuric acid and then chloric acid, and then we'll see. So I have for you here H2SO4. Then I have for you H2SO3. Then I have for you H2SO2. So those are hypothetical. At least this one is present, this one is present, this one maybe is not present, but at least you get this one. This one here, our standard. Remember I said the standard for the naming. So then if you go from here, less one oxygen, what you use? S, correct? So therefore this is sulfuric, and then let me just maybe another color here, ic acid, correct? And then the other one here is will be sulfur, and then just with the blue color makes a lot of sulfurous acid. Makes sense? How about the third one? Will be what? Somebody will tell me? Come on, guys. This is less one oxygen. What we add? That's less. Will be what? Sulfurous, because that's from the previous one came out. Sulfurous acid. Make sense, guys? So let's take another one. Let's take another example. So everybody has it? Everybody has this? That's not in the PowerPoint. That's not inside the book, eBook, or a text, any, even temporarily it's not in. But I want just to show you how you can manage those. So always there's a master map to name those. The standard one, ic acid. The less the standard is acid. The least than the acid will be hypo acid, correct? So let's look at this one here, and we have, you can name this one here. This is chloric acid. Chloric acid. This one here have more than one oxygen more. This one here has less, and this one here has the least. So that's our standard. The main thing is you have to pinpoint where is your standard acid. This is our standard acid, correct? Because it's standard acid, then it will be chloric, from chlorine, chloric acid, correct? Now, this one will be what? Somebody will tell me? Less one oxygen. So it will be what? Correct. Will be chlorous. Perfect. Sounds not Monday today, it's real Wednesday. So chlorous acid. So ic acid, chlorous acid. And this is, again, is less one oxygen will be hypo. Perfect, perfect, perfect. It's really Wednesday today. Is hypochlorous acid, correct? Now, how about it is one more, one oxygen, not less. Well, in this case, hyper, correct? You know, somebody has um, hypo pressure and then hyper pressure. So hyperpressure means the blood pressure is, or the pressure is very high. Hypo means least, so less. So this one is, instead of hyper, the opposite of hypo is hyper. So this is too much. So they said, well, we'll take this one here out, the hyper, correct? So here it is. Let me just, so take this one here is hyper. So opposite of hypo here, hypo and hyper, they are opposite to each other. So, but they said, well, we'll not take this hyper out. We'll say per what? Per perchloric acid. Perchloric acid, because this came from this, from the standard above the standard. So this one here will be perchloric acid. Now, the salt is the same thing. The salt, the anion of those acids, correct? The anion, if you dissolve those one here in H2O, you get an anion of those. So let me just show you how to name those salts so you'll be aware of this. That's coming from the acid itself. So can I take this one out? Take this one out? Okay, I'm taking this one out. And look at the salt of this one here. If I have those are, this one here, what we call it, perchloric, correct? This is perchloric acid. This is chloric acid, HClO3. This is chlorous acid, which is HSClO2, and this is hypochlorous acid, and this is HClO. Now, we have this, we have this, we have this. Oops, sorry. Suppose to do this here. Hold on, I'm just writing for you. It is HClO2. Okay, guys, so we have, if I let those react with H2O, so let them react with H2O, dissociating H2O to get the anion, to name the anion. So what we are getting here out of this, we are getting the hydronium ion. I'm not balancing, just to let you know that this is the hydronium ion. That's emphasize that we have an acid. Then we have the corresponding, this one here, plus the anion, correct? So the anion of this will be ClO4 minus. This is the general reaction here. And let's put the anion here. Maybe the anion here. So ClO4 minus, correct? That's the anion. And this is ClO3 minus this ClO2 minus this ClO minus. Correct, guys? So this is the anion, which is, this is the anion here. Correct? All those are anion, negative, 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 negative. Now, how we name this? Well, let's look at this. The ClO4 minus cold is coming from perchloric acid. So it will be perchlorate ion. This is ion. ClO3 minus will be chlorate, chloric acid, chlorate ion. And you see ATE at the end. ATE ion. Ion, correct? So how about ClO2 minus? Well, this one here, we said what? Because it's less than the chlorate, the naming of it will be not as or something. That's for the acid. This one will be 8, will be here, chlor. Oh, sorry. Will be chlor, and then ITE, ITE ion. Chlorite, what we call it? Chlorite ion. The standard acid, chloric acid, the anion of it, chlorate, correct? And ClO minus, this will be hypo, correct? Same thing we have per, hypo, chlor, and then ITE, ITE ion. Okay, guys, so that's just to let you know that the anions of those acids will change naming 8 or 8 or hypoite or per whatever chloride. If that's it can be a bromic acid, bromate ion, and so on. Okay, guys, that's just to show you those anions, how you name those. Okay, guys, that will be the naming of the acids in general. So that's about it. That's the most important thing about naming those acids. We'll go for base, how to name bases. Any question you have so far? Any question about this? Any question? Take it out. Okay, let's take it out. And you have the recording there available, so you can go back and look. Okay, guys, here it is. Now we'll be naming our bases here. Naming bases. Well, the basis is always because you have the OH hydroxide and then the metal. So like the one they have the first tab here with OH, correct, anion, and with metals that have one charge. So what you call this one here, like KOH, BaOH2, AlOH3. Well, it turns out always you start with the naming of the metal itself. So you name what? The metal itself. So this is the metal here. This is this. This is this. Those are metals. And the hydroxide, those will be cation, and the hydroxide is there. So this will be potassium hydroxide. not hydro and then pause and oxide. That's a little bit very funny, but you cannot pronounce this. Potassium, hydro, pause a little bit, and then say oxide. No, just hydroxide, because it will be two vowels here, right? Take one out, so hydroxide. That's one vowel. So potassium hydroxide. This is the Ba group number 2. That's barium. Barium hydroxide. This one here is aluminum hydroxide. Now, if we have with one that have only one charge, then how about if we have multiple charges, okay? With metals that have multiple charges. So the next type of naming is the with hydroxide and with metals that have multiple charges. Then we have to go to our Roman numbers. Remember the Roman numbers? Can I take this one here? So now we'll switch from 1 to several. Everybody has it? Okay, good. Take this one here, and then number 2 here of the naming here with the hydroxide and metals with multiple charges. And typical is really typical is the transition elements. Typical these metals are transition metals. Those are in between the big in between group, okay, in between, so or the B group. So if you look at this, so I give you an example here. We have iron, here it is, and we have okay, another example. So how we name this? Well, since we have this multiple charges, multiple here charges, so then we have to introduce our what? Introduce our Roman number. So this is iron, and this the 3 is coming from what? From the iron. Iron 3 hydroxide. And this is iron. This is 2 here for iron 2 hydroxide. Okay, guys. So if I will give you another one, you can tell that's chromium can come in this one here, and chromium can come. So what we call this one here? This one here will be what? Chromium 3 here, correct? 3 is coming from chromium. Chromium 3 hydroxide, correct? How about here? The 6, correct? 6 will go coming from the chromium. So chromium 6, 5, 6, Roman number, hydroxide. Everybody's following here? So that's multiple charges. Now the third type is a very unique common names, very unique common names we can use for some bases because they don't have the hydroxide per se, so they don't have the peroxide. So common name bases, so bases with common names. So can I take this one out? Everybody has it? Good, perfect, perfect. Perfect. So let's do this one here. We say number 3, bases with common names. Okay, those are mostly common names. Those are mostly our friend here, Luis, bases. Now they have extra what? They have extra VEs. They have extra valence electrons, so they can donate them. Extra that can be donated. That's Lewis donation of this extra and they'll be donated. So those VEs can be donated. So such as, just to show you how they look like. This is what? This is a base too, because it has, although it's amphoteric, but it's a base. H2O is a base. So what you can tell common name for it, that's just H2O. You say that's just dihydrogen oxide, or just water. Okay, same thing here. The real name is dihydrogen oxide. That's the real name. IOP, International Union for Pure and Applied Chemicals. This is a big union that's naming those compounds here, and this is the real name. So ammonia has extra 2 sets of lone pair. Okay, so ammonia is a base, but we cannot say ammonium hydroxide. I mean, it can connect itself, but ammonia is a base as well. It's a gas base without the hydroxide. Okay, so this one has extra. See, they have extra. All of them, they have extra what? All of them, they have extra VEs, which can be donated, correct? So this one here, we call it the IOVC name here. So will be nitrogen here, trihydride. It has 3 hydrogens, trihydride. But what's the common name is what? Somebody will tell me. That's the common name here. That's common here. Common name. Here and here. Ammonia is a common name. It's a base, but there is no hydroxide in it. And H2O, there is no hydroxide. It has a hydroxide, but you cannot say hydrogen hydroxide. You cannot say hydrogen. So you look at the H2O like this. This is hydrogen, and then comes the idea that's hydrogen, and this is hydroxide. This is by far is a big mistake. So don't do that. So this one, the name is not correct. Just common name of it. The IOBC name, the really standard name from the International Union for Pure and Applied Chemicals. They say this is dihydrogen. Remember, this is 2 hydrogen, dihydrogen oxide. That's the real name, or just tap water, just water. Ammonia, the same thing. It's the real name, IUPAC name for it, standard name, accepted name. Nitrogen trihydride. Nitrogen trihydride. Okay, guys. So those are the bases we have to watch, and I can just refer to the. If you are done, I will show you some other ones. Phosphine is there, ether is there. So some other compounds, they are there and they are bases, but you cannot give them a name of hydroxide. Pyridine, name as well. So can I take this one out? Everybody has it? Okay, good. Let's take this one here. I want to share with you the those common names. Here it is. That's barium. Here, if you look at those here, guys. Whoops, sorry. Here they are some of those common names bases. Those are Lewis bases. And as you can see, you cannot name them as a usual base with the metal and hydroxide. So here those are special Lewis bases, and they do have special name, correct? Dihydrogen monoxide, and then we have dihydrogen um, dioxide, and then we have ammonia, which is nitrogen trihydride, and you have ether, diethyl ether or ethoxyethane. We have phosphine or phosphorus trihydride. We have carbon monoxide or carbonic oxide. So those are, you don't have to worry about, but at least you know that some bases, they go off the record of hydroxide. You cannot say this hydroxide. And they are not really obvious to be, unless you write the Lewis dot structure and prove to yourself they have extra valence electrons can be donated, then they are Lewis bases, correct? Lewis bases, those are bases. They have extra valence electron at the central atom, which can be donated. Any question about this so far? Any question? Okay, so let's get this okay, now we'll know about acid and base acid base constant, acid base constant, acid base constant. So learn about something called acid base constant. Acid base constant. Well, if I have a weak acid, usually weak, just constant. That's especially for can be for strong and weak acids bases. So, for example, if I have, and then we'll come and see the strength of each acid. If I have here HF react with H2O, correct? That will give me here, this is a weak acid, with double arrow, the weak acid, and you will see that this one here will come donating to this. This is the donor here, that's acid. This acceptor, that's a base. So you have H3 plus the fluoride ion. And this is, we have Ka. K what? Ka. The we call it acid dissociation constant. Acid dissociation constant. So here we can put dissociation constant. So the Ka will be the ratio between the product, the same thing here with chapter 8 equilibrium, remember? The product here, those are the products, over the reactant, HF and H2O. Now, if you look at this very carefully here, and look at the subscript here, then you can tell this is aqueous, this is liquid, this is aqueous, this is aqueous. So we'll keep the aqueous there. So keep aqueous, untouched. Number 2, discard liquids. Discard liquids. So this is liquid, so this is a liquid here. So all of them are aqueous, aqueous, aqueous. I'll keep this one here, I'll take it out. So the dissociation constant of the this acid will be Ka. Dissociation constant of acid will be the hydronium ion, so I'm keeping, multiplied by the fluoride ion divided by the acid HF. Only the aqueous are kept inside. The liquids are out. So this is the dissociation constant of HF. Okay, guys? So now we can do it for the same thing for a base. We take an example of a base. This is a weak acid. So it has a double arrow. We'll talk about weak acid first. Let's finish the base. So can I take this one out? Take it out. I'm taking this one out. And I have a base. For example, I can take any base you want, and you can tell that's a base will be say aluminum hydroxide. Can dissociate in H2O to give us Al 3 plus 3 OH minus. So now let's look at this one here. AQ, AQ, AQ. So this will be KB, not acid dissociation constant, base dissociation constant. So base before the dissociation constant, correct, will be KB. So the KB here will be the products over the reactants. Watch out for that. Watch out now. Multiplied by OH minus. Now, since it's 3 mole here, if you have 3 mole, the 3 will come out as an exponent divided by Al. Excuse me. Thank you. You see the 3? The 3 came out from here as a number of moles, came out as exponent here. All those are molarities. All those are molarities. Can you see that? So Kb is aluminum 3 plus OH minus AlO3, the whole thing. Those are aqueous. So we kept all the aqueous there. If we have a liquid, we can take it out. Okay, guys? So that's a Kb. Now, how in the world I will know which one is strong, which one is weak? Well, it turns out to be, can I take this one out? Everybody has it? So now, strength of an acid and base. So strength. So weak or strong. So let me show you here. There is a table. You can look at the table and see how the values is. But the main thing is, from the table here, if Ka or Kb greater than 1, then you have strong what? Acid or base. If Ka or Kb less than 1, you have weaker or weak acid or base, or acids or bases here. Okay, guys. Well, we did not have a Ka equal. You have to have them both either above 0, above 1, okay, above 1, and lower than 1. So therefore, we can tell this is aqueous. So a strong acid or basis is recognized by, let me see here. This one here will favor the products. So favors Ka or Kb greater than 1, favors the product side. And this one here will favors the reactants. So the whole thing is favors if Ka greater than 1, strong acid, and it is recognized by almost one arrow, almost one arrow is used. Here, only double means 2 arrows are used. So let's look at an example here. Let's look at what example. I'll do acid and then I will do basis and see what will happen. Okay, guys. So can everybody has this? Okay, let's take this one here and let's look at acid. I have here one of the strongest acid, sulfuric acid, correct? And sulfuric acid in H2O will have something looking like this: 2H plus SO4 2 minus. Of course, the 2H plus is literally 2H. That's what it means. But I'm not balancing, just to show you how this works. So now this is one arrow, almost one arrow. Now the reverse reaction is almost very, very tiny. So you can write this one here, just very, very tiny. So just drop. Well, let me just write it again. So it does not want to draw very well, but trying to. So maybe like this. See here? And the red one here is very thick this way. So this one here is a strong acid. However, if I have phosphoric acid, which will give us 3H plus PO4 3 minus, guess what? Identical double arrow. Identical ones. So it is okay, guys. So this is weak acid. Just looking at the double arrow here. So here it is. Double means 2 arrows. So that's from just looking at this without even testing the table values. Right? But we'll go and test the values there. So this is the same thing. If I look at the basis, the same thing. We'll have a double arrow if it's weak, one arrow if it's strong. So let's take the the bases and look at the whole thing. Can I take this one out? Take this one out? Everybody has it? Okay, let's take this one out. Let's look at the bases. Now, if I have potassium hydroxide, correct, goes like this, potassium plus OH minus, and then just a small tiny. This is what? Strong base or strong or weak base? This one what? Strong, correct? Strong base. But if I have another base that's really very weak, such as ammonium hydroxide, identical double what? Or iron hydroxide, iron 3 hydroxide. So those are what? Weak bases. So without looking. Now let's look at the values, and let's look at the what we can consider strong, what we can consider. This is just from the looking at the whole equation of this dissociation and tell if they are strong or weak. Okay, let me take this one here out. Everybody has it? So we have acids. 7 acids are strong. All the rest of acids are weak. So only 7 acids are considered to be strong. Considered to be strong. So which are those acids? Well, it turns out group number 7 there, HCl, HBr, HI. Not the HF. HF is weak, correct? ClBrI. So those 3. Then you have our 2 friends here, hydrochloric acid, correct? Or 3 of them, hydrochloric acid, nitric acid, and sulfuric acid. Those are strong acids. Okay. Then we have chloric acid and perchloric acid. How many we have? Yeah, 1, 2, 3, 4, 5, 6, 7, 8. 8 we have. Yeah, 8. Correct, guys? We have 8 of those strong acids. Correct? The rest of the acids are weak. All the acids you can imagine will come to your thinking. They are weak. So the rest of the acids, the rest of all acids is weak. Okay? And we did do a 7. We have 7 or 8. Sulfuric, phosphoric. Yeah, this is 8. Yeah, 7 if we don't have perchloric, but perchloric is strong too. So let me. What's that? Which one I wrote twice? The first 2 twice? Oh yeah. Okay, that's. I said this. I count them 7. Okay, that's. Thank you. So because it's can both sides, so that is correct 7. For me, it's still Monday. So anyway. So always okay. Thank you. But anyway, so those are 7. So all the rest are what? Weak. Now we can go and look at their values. You'll be astonished to see their values so large. So that's the acids. How about the bases? Let's take this one out. Everybody has it? So now the bases, group 1, group 2 are strong. All the rest of the group in the periodic table are forming weak bases. So it is strong bases are coming from the metals of group 1 or 1A and 2 or 2A. So for example, lithium hydroxide, that's strong, one way, lithium plus OH minus, correct? That's plus here. This is group A, 1A or 1, correct? 2 or 2A is calcium hydroxide, one arrow, okay? So that will be calcium plus 2OH minus. And the small tiny maybe here, small tiny, it's not really arrows. So those are strong. Group 1A and 2A, those are the only one are making strong base. All the rest of the, correct? Then here, all the rest of the bases are weak. So guys, they are very weak. So that's, I mean, I can tell you this, like aluminum hydroxide, for example. Aluminum hydroxide, iron oxide, aluminum hydroxide, iron hydroxide, 3. This is 3 here because this has more than one charge. Aluminum hydroxide or iron 3 hydroxide, those are weak. But all the group 1A and 2A making very strong bases. The rest of the metals will make very weak bases. Okay, guys? So now let's go and look at the values. I might just, if you allow me, I might just Google here. Google here. So, oops. Can I take this one out? Everybody has it? Everybody has it? Okay, so let's Google here and look. Not Googling. I'm sorry. Let's Bing here. We are Binging here. Not Googling. We are Binging here. Microsoft Bing. Let's Bing about the strong acids, comma, base chart or list. Here is the chart and here is the values. I need to see the values. Maybe this one here. They have the values. If you can see the values, let me know. I need to see the values for every single values. So which one has the values? I think this one here. Okay, so the Ka value, correct? And that's the acid, and the Kb the opposite. So if I take, well, they put okay, that sounds good. So if I want to take this one here and make it bigger, guys, look at the Ka of hydroiodic, hydrobromic, hydrochloric, nitric, greater than 1. They don't even give you the value, correct? Now, if you go for oxalic acid, less than 1, 10 minus 2, This one does not give you, but there is chart will give you really the real value. So as you can see, greater than 1 is always a stronger acid. So I don't know why is, let me, just get through here. They don't give the value very well, so I wish they can give you the value, but I can send you the with the value. So strong acid base chart. Yeah, those are charts without the values, but you can look at the chart, some charts with real value, so you can get the sense of how much is the value is, how much is the value is. So yeah, here's the value, guys. This is much, by far is much better. Let me just take it in. We have plenty of time. We are, oh, what is this here? So they prevent us from copy it, but we can get around it. So it is. Sometimes they can't let you snip it out. So it is copy, and I'm pasting it in the large. Here, guys, look at this. Here we have the values. The perchloric acid is very strong. You see here? It does not even give you the Ka value. All those, they have no values, all those strong ones. But then the weaker one, they have what? Minus exponent, less than 1. So, but anyway, so you get the idea. And the same thing with bases. The bases, if the value 1 and above, that's above 1, it's strong base, and the less than 1, it's weak base. So you get the idea. So just I want to share that with you so you get this one here. So, okay, guys. So now we'll get out of this. We went to the strength. We went to the whole thing. Now we are going to, we went to conjugated base, strength of the acid, strength of the base. We talked about this. Here's the values, but without the Ka value. Yeah. There's here one. There's a good one here. Look, here give you even the one. So here the with the value. So that's a good one here. So maybe here, guys, bear with me. To get the, so what we mean by strength of the acid or bases is their ability to dissociate in H2O, correct? Their ability to dissociation. Okay, it is. Now let's look at the strongest one. Perchloric acid has no value. That's, I saw it in the, but look at the hydrobromic acid, 10 power 9. 10 power 9 is in the what? In the million or billion range? That's in the billion range. Can you see that? 10 power 9 is 3.2 10 power 9. That's in the billion range. Those are very, very large numbers. And you can see how the numbers are. So those strong acid, they will give you very large number. Let's put a note here. Here it is. So those are strong acid, we said. 1, 2, 3, 1, 2, 3, 4, 5, 6. The chloric acid is not there, but chloric acid is there in another table. But anyway, those are 6, 6. And if you look at chloric acid missing, but it should be there. Those are, see, large values, large Ka values. So this is strong acids. Okay, guys, so those are very strong acids. And the same thing, you can check the bases. If the Kb is very strong, then they are strong. So the idea is what? Let's ask ourselves, what do we mean the strength of the we say this acid or base are strong or weak. So this is the ability to dissociate in H2O. Okay, if they dissociate 100%, so let me take this one out, and take this one here out too. It does not want to take it. So okay, guys. So let's look at this. The weak acids. Weak acids. Strong weak acids here. It depends on so the strength is weak acid or strong acid. So both of them here. Maybe we'll take all this out here. So the dissociation of an acid or a base in H2O will gives the information about its strength. That's what it means. That's what if the dissociation constant, then if Ka and Kb greater than 1, strong, correct? And if Ka and Kb less than, less than 1 here. Okay, so less than 1, this is weak. That's all this, the whole thing. And we will stop in this weak and strength, and we will go for the next step. We can go and look at the titration. Let me see here. Can I take this one out of the acid? So that's I think enough information about this. So now, before we go, let's do the dissociation of H2O. Okay, let's do the dissociation of H2O. So here it is. H2O is a very unique compound that's called amphoteric. H2O is an amphoteric compound. What does it mean? Like metalloid. Metalloid can act as a metal in some conditions, and they can act as non-metal in some conditions. So it's a compound. It means that can act as an acid in certain conditions, correct? At certain conditions, as well as it can act as a base in or under certain conditions or other certain conditions. Okay, guys, so this is amphoteric. Anytime you get the word amphoteric means it's a compound that can switch character. So it has a dual character. It can be acid, can be a base. Okay, guys. So now the the dissociation of H2O inside H2O itself, called auto ionization of H2O, auto dissociation of H2O. So can I take this one out? So we can talk about auto ionization of H2O, or auto dissociation of H2O. Now, since it's amphoteric, we have four minutes. Cool yourself down. Don't make yourself ready to go out. So cool yourself down here. So we have H2O. This is an acid. Plus H2O. This acts like a base. So the acid will come and give one of this one here. Double arrow is a weak. H2O is a weak acid and weak base at the same time. So it will be H3O plus. That's a conjugated acid. It was a base that's accept H proton, and this is OH minus. And this is, instead of Ka, we'll say Kw. So the Kw here is the dissociation of H2O. Constant. So it was found by experiment that this concentration here is equal to 1.0 10 minus 7 molar, and this one here the same thing, both of them 10 minus 7. So the Kw then will be correct. This is here liquid, aqueous, correct? So the Kw is H3O plus multiplied by OH minus, and we have H2O multiplied by H2O, product over reactants. However, this is liquid, aqueous, so we have to get rid of those aqueous. So then our Kw here will be H3O plus multiplied by OH minus. And putting the number here, 1.0 10 to minus 7. Don't worry about the units. 1.0 10 to minus 7. And the Kw will be what? Somebody will tell me. 1.0 10 minus what? 14. This is the value, again, Kw here. 1.0 10 minus 14. I'll stop here, and then we'll come to look at the titration. So this is a constant of H2O, 1.10 minus 14. So we have just the next week. Next week we'll come and finish this chapter, and then we are done, and then we can make a review.